So the next topic is public key cryptography, and public key cryptography means you have two keys. One is called the public key, and the other one is called private key. I tend to use the term private key and not secret key, because secret key is something that I use in the context of symmetric cryptography, whereas in the context of public key cryptography, I use the terms public key and private key. Okay, so the interesting thing about public key cryptography is that you have these two keys, and in a sense, one key is like the inverse of the other key. Okay, so the key that is called private is the one that is needs to be protected, and so each principal has their own private key, and then the corresponding public key is something that can be public knowledge. It doesn't have to be secret, right? So this contrasts with symmetric cryptography, where the key always needs to be a secret, right? So whereas here there are two keys, one key needs to be a secret, the other one can be freely given to everybody, right? And going back to the picture, this is the picture kind of illustrates how the public key cryptography works. And what it shows is that each principal, or user as you may want to think about, has a pair of keys. One is the public key and the private key. And so if I want to send a message to Bob, then I'm going to pick Bob's public key, and I'm going to encrypt the message using Bob's public key and transmit it. The meaning of encrypting using public key is that it can be only decrypted using Bob's private key. And because only Bob has his private key, only Bob will be able to decrypt and see what is there in the message. Okay, so that's how the public key cryptography works. The public key cryptography you can not only use for transmitting a ciphertext that nobody can figure out, right? So in particular, the picture that we just looked at is one that protects secrecy of the message, or confidentiality of the message. But you may be interested in protecting the integrity rather than the confidentiality. Okay, in that case, what you do is you take the recipient. So the way this works is that Alice wants to send a message to Bob, and in this case, Alice is going to encrypt it using her private key. And now you realize that because it's encrypted using a private key, it's going to be, you can decrypt it using Alice's public key, which is available to everybody, which means that anybody can figure out what is the text that's being transmitted. So confidentiality is not being protected, but integrity is being protected, because the message could have been created only by someone who already has Alice's private key, and by our assumption, only Alice has Alice's private key, and therefore this message could only have come from Alice, right? So the receiver can verify the integrity and authenticity of the message, right? Authentic in this context means that the message is coming from whoever is it's supposed to be coming from, right? So it's the message says, this is a message from Alice, and you can verify that, right? Well, it is from Alice because it is something that I can decrypt using Alice's public key. So, so this is, these two ways of using public keys leads us to talk about the distinction between encrypting versus signing, right? So the first picture shows encryption, meaning that the data that you transmit remains confidential. The second one is more like signing, because it makes sure that because you're able to verify who actually sent you the message, right? So when you think about signing in the physical world, signing is all about somebody, it's about verifying the person who actually signed the document. And so by encrypting it using her private key, Alice is essentially digitally signing the document. And so that's why we talk about the second way of using public key cryptography as a signing operation. Okay, so we'll talk about digital signatures more later on. So, but I just want you to know, realize this difference between two ways of using the public key cryptographic algorithm. Okay, so there are many multiple public key cryptographic algorithms, just like we saw many other secret or symmetric cryptography algorithms like DES and AES and RC5 and RC2. Similar to that, we have many different public key algorithms. Some of them are, one of the most famous ones is the RSA algorithm that I'm going to briefly discuss now. There are a couple of other algorithms that you may have heard about. One of them is based on the problem of computing discrete logarithms. Okay, so that's often used in the context of doing digital signatures. And then there is another algorithm that's based on what are called elliptic curves. Right, so they are all different public key algorithms, and but I'm going to talk about just RSA because it's something that is somewhat easy to understand at some level. Okay, so what is RSA? Right, so RSA is an algorithm that relies on the difficulty of integer factorization problem. Okay, so when you have very large integers, factorizing these very large integers is a difficult problem, and people have studied this for hundreds of years, right? And they haven't found a good solution. And so it's believed that it is a hard problem that cannot easily be solved, and that's why we have built this cryptographic technique on the basis of this technique. And to take a step back, the whole notion that there could be this kind of asymmetric cryptography, right? That's the term that's sometimes used to talk about public key cryptography. It is asymmetric in the sense that you're using one key for encryption and a different key for decryption. And the possibility of asymmetric cryptography itself, nobody, it's just so hard to even imagine. Before somebody came up with the idea, people couldn't even imagine that such a thing is possible. But once you know it's possible, then many times in science, when you know that something is possible, it becomes, you can then figure out how to do it. But most of the time, you don't even think something is possible, and therefore you don't even think about it, right? So in this case, it relies on some properties of modulo arithmetic on very large numbers, right? So typically when we talk about RSA algorithm, we talk about keys that are many hundreds of bits to thousands of bits, right? So these are very, very large numbers, not like your 32-bit integers or 64-bit integers we have been talking about. These are much, much larger integers, okay? And what we do with them is that we don't do just normal integer arithmetic, because if you do normal integer arithmetic, then there will be overflows, right? So if you take a 200-bit numbers, you multiply them, you'll get a 200-bit number, right? So that's not good, because if you want to do computation, you want to work with a fixed number of bits, okay? So the typical solution is to do everything modulo some base, meaning that you do the multiplication and then you take the result, you divide it by a base, and then you keep just a reminder, right? So that's the modulo arithmetic. And in the case of RSA, there are the encryption and decryption operation are conceptually very simple. So what you do is to encrypt, you take your message, and your message in this case is simply a number, right? So it's in this case, you know, if so that's why we say that the alphabet or the input is something between 0 and n minus 1, where n is the base of your modulo arithmetic. Okay, and then to encrypt it, you take the message, you raise it to the exponent e, and then you know, of course that could be a very large number, and you do the mod, and then you compute the result. Okay, to do the decryption, you take the ciphertext and you raise it to another modulo called d, and you can think of E and D as somewhat like your public and private keys, right? And then you get the result. So if you do the substitution, then the result here is basically m raised to the power e, then raised to the power d, which is m raised to the power ed. And in order for you to get the original message at this point, right, because you did the encryption and the decryption, so you want this to be the original message, and that is the property that you need. And RSA algorithm is all about you know, choosing E and D in such a way that this property is satisfied, right? And in addition, of course, you need to make sure that you know, somebody who knows E cannot figure out D and vice versa, right? Because if somebody knows the public key, they shouldn't be able to figure out what is the corresponding private key. So those are the two main conditions that that this identity hold, and that, you know, knowing one of the keys, you won't be able to figure out the other number. Okay. So of course there are a few other assumptions. You know, because you need to compute n to the power e and n to the power c to the power d and so on. Those shouldn't take an inordinate amount of time. Okay. So the way the algorithm works is, as I said, you know, it depends on the problem of difficulty of factorizing integers. So that shows up in this chart. So you select two large prime numbers, p and q. And once again, these are, when I say large, remember that it's supposed to be hundreds to thousands of bits. So these are very, very large prime numbers. And then you compute the product of this p and q, and that is, you know, you start with that, and then you compute this quantity called phi of n, which denotes the number of numbers that are relatively prime to each other. And for if p and q are prime numbers, it can be shown that phi of n is just p minus 1 times q minus 1. And this phi of n becomes the base that we talked about in the previous chart. No, I'm sorry. No. The n remains the base for the modulo arithmetic, but phi of n is used to calculate d given an e. Okay, and so you have to select the exponent e in a certain way, in such a way that it satisfies this condition that the greatest common divisor of phi of n and e is 1, and then you can figure out what is d based on this formula d equals e, the inverse of e when you use modulo arithmetic for the base phi of n, and then you can talk about what is a public key and private key. I'm not going to tell you exactly why this property m raised to the power e equals m holds in this case. If you're interested, you can, you know, easily look up. It's not that complicated to figure this out, but I again, in the interest of time, I'm not going to go through that in much detail. So once you have all of this in place, then you know, encryption is done. Given a message m that's less than n, then you do this m to raise to the power e, and again C raised to the power D in order to decrypt. Okay, so what I want to say now is, so we talked about, when we stop.